that, but I'm not drawing the entire mechanism. Let's just draw this. So this is after the quench with water. But then again, if we want to take a secondary alcohol and oxidize it to a ketone, you could literally use any of the conditions that I've taught you. You could use chromic acid, PCC, Swern oxidation, a Des-Martin periodinane. There are many others that could be used. I've taught the class long enough to know that something that students tend to do, and I don't blame them at all for this, I would do the same thing, is they tend to gravitate towards the ones that are fastest to write, because everybody gets tired of writing out the same things over and over. So, my students really like PCC. It's really quick to write down, and I don't blame them one bit for that. So there you go. And we could write here, or a Swern, or a Des-Martin periodinane, not DMF, got DMF on the brain. Or you could use the Jones reagent, right, which is just anything that, I don't know why I put an apostrophe there. The Jones reagent, which is just a way to make chromic acid. Jones reagent's really old. That's really old chemistry, but still commonly used. I did it in graduate school. I had to make a giant batch of the Jones reagent. All right, let's take a look at 12.24b. We're also starting with an aldehyde here, and we want to convert that into a ketone. Now, we've seen this how many times today? This is the third time, right? I had it in the slides. We looked at it in the last problem, and now we're looking at it one more time. So same type of rationale here. We're trying to add one carbon-based group, right? We want to add one carbon to the molecule. So, I think, all right, well, I'm going to start with methyl magnesium bromide, followed by treatment with water. And that is going to give me not an aldehyde, not a ketone. It's going to give me an alcohol, isn't it? Gives me a secondary alcohol, but then all I have to do is oxidize that. Let's choose the Swern just to be interesting. So dimethyl sulfoxide, you guys know what DMSO is, right? It's this, dimethyl sulfoxide. Draw a proper Lewis structure. Dimethyl sulfoxide, oxalochloride, which is COCl2. So oxalochloride is this. So you have two carbonyls, you have two chlorines like that. And then in the second step, you treat it with triethylamine. And triethylamine is just an amine that has 1, 2, 3 ethyl groups on it like that. There we go. Any one of those ways would work. Any one of those ways is perfectly reasonable. Let's continue on with our practice. I want to be doubly sure I'm still recording here. There we go. Let's take a look at one of the questions that deals with another question that deals with synthesis. So here I'm going to give my students a little bit of time to try this one. This is 12.25, and I want to start by taking a look at A. So 12.25A. There we go. So here it is. We're making a ketone. So I want everybody to take a look at that one. And then we're also going to try this one. We're only starting it with 2 measly carbons, and we're ending up with a whole holy host of them, aren't we? I want to draw my ketone incorrectly here. There we go. So I'm going to give you a few minutes to try both of those. And then we're going to come back. I'm not going to take a break, but I'm just going to go grab a drink of water. And we're going to take a look at those. All right, let's start with the first one. You can see that there's a change to the carbon skeleton here, right? We're starting with 1, 2, 3, 4, 5 carbons. Then we have 1, 2, 3, 4, 5, 6 carbons. So we're adding 1 carbon. We're also making a ketone. And in order to make a ketone, well, what are our options? We can oxidize an alcohol. Really, we could do ozonolysis, which is obviously not what's happening here because the carbon skeleton is getting bigger, not smaller. And so we're going to have to think about this one in terms of retrosynthesis. I think that's the best way to approach this. And the way I would approach this one is I would say, well, if I want to make a bigger carbon skeleton, oops, where did my, sorry, I'm having some problems, some computer problems here. There we go. All right, so if I had $1 million, if I had this aldehyde, if I had that aldehyde, then all I'd have to do is take that and treat it with methyl magnesium bromide, oops, followed by water, right? And that would make the alcohol, right? And then third, I would just do an oxidation, right? And that would give me the ketone. So then the question becomes, how do I go from here to here? Well, I can't go from there to there directly. There's no way to go from an alkene to an aldehyde directly. However, I can think about an alcohol, right? What if I had this alcohol, right? All I'd have to do is oxidize that, and that would make the aldehyde. And I think that everybody knows how to go from here to here, right? That's just an anti-Markovnikov addition of water across the double bond. So borane and THF, followed by treatment with hydrogen peroxide and sodium hydroxide. That gives us this guy that we wanted. We're going to oxidize that. I'll use PCC because we want to stop at the aldehyde. So PCC and dichloromethane, DCM. Again, that will produce this aldehyde. There we go. That produces the aldehyde. There we go. And then for the ending, well, I'm kind of running out of space here. And you know what I'll do is I will move this down. There, why don't we just move that out of the way? And then we're going to take this and we're going to treat that with methyl magnesium bromide, followed by treatment with water. And that's going to give us an alcohol, isn't it? We're going to end up with a hydroxyl here and that 1 carbon added. And then we're going to treat that with whatever oxidizing agent we want because we've got a secondary alcohol. It's going to stop at the ketone. Let's choose Jones reagent just for fun. Let's try chromium trioxide, acetone, and aqueous acid. There we go. And that's going to oxidize it to the ketone. And again, if you chose the SWERN or the PCC, anything like that, it's totally fine. There we go. So how many steps is that overall? We have 2 steps here. 1, 2, 3, 4, 5, 6 steps total to go from this alkene to this ketone. So this is 6 steps. So not an inconsequential number of steps. Okay, definitely some challenging chemistry there. Well, with that in mind, let's try this next one, which is definitely challenging. We have a huge change to our carbon skeleton, don't we? If we're going from, I'm not going to be able to do that copy. Try pasting it on here. There we go. All right, I'll move it on over here. So again, this is question 12.25 that we're still working on, 12.25. I want to start with acetylene, and I want to make this this ketone. Well, boy, I'm changing the carbon skeleton a lot here, aren't I? Because I'm starting it with 2 carbons, and I'm ending up with 7 carbons. Huge change. Well, in terms of, ways that we could make this and end up with only this 1 ketone, because there's probably several ways we could make a ketone. But in terms of retrosynthesis, if I think about this in terms of a Grignard, which I like to use when I'm changing the number of carbons in the skeleton, if I had 1, 2, 3, 4, 5, if I had this aldehyde, right, all I'd have to do is treat that with ethyl magnesium bromide, water, and then oxidize it to make to make the ketone. So how would I go from, this 2-carbon acetylene molecule to 1, 2, 3, 4, 5 carbons? Okay. Well, I could think about treating that with if I had, sorry, I'm just thinking out loud here. If I had this molecule, if I had this alkyne, then all I'd have to do is an anti-Markovnikov addition of water with 9 bbn, right? And that would give me the aldehyde. So then it becomes a lot more simple. How do I go from here to here? All I have to do is add 3 carbons, right? I treat this in the first step with sodium amide, and then I treat it with propyl iodide. So 1, 2, 3 carbons, and then an iodine. And then that would give me that compound. So I have 1, 2 carbons here, 3, 4, 5, like that. And then in the next step, I can treat this with 9 bbn, and then H2O2 and sodium hydroxide. I'm not going to draw the enol that's formed. I'm going to assume that you know how to draw the enol. And you would end up with 1, 2, 3, 4, 5 carbons total. And that would tautomerize to give you this aldehyde, right? Then from there, you can treat this with ethyl magnesium bromide, the Grignard, followed by water. That would give you the desired alcohol. So that would give you enough carbons, and you'd have this alcohol. And then you can just oxidize this with whatever you want. Let's choose Desmartin periodinane, which is usually done in dichloromethane. And there you go. How many steps is this? Let's take a look. We've got a total of 1, 2, 3, 4, 5, 6, 7. So that's a 7-step problem. 7 steps to get from our starting material to our product. Let's take a look at the next one, C. So this is 12.25 C. I know that it might sound or seem daunting to go over so many problems, but again, I've taught the class enough to know that this is the best way to master, all the different reactions that we've looked at, and we've looked at a lot of reactions. And then after this, we're going to take a look at a problem that involves drawing a mechanism. So 12.25 C is the one I wanted to look at next. We're starting it with this simple aldehyde, only 4 carbons, and we're making another ketone. Well, the reason we repeat this reaction so many times, this type of reaction, is because, or this type of synthesis, I should say, is because it's so important in organic chemistry, right? You're adding a total of 2 carbons to the molecule like that. So you need to know that how to use a Grignard reagent, right? Ethyl magnesium bromide, followed by treatment with water to give you this secondary alcohol, and then an oxidation using PCC and dichloromethane. Again, if you chose something else, there's nothing wrong with that, as long as it is an appropriate oxidizing agent. All right, from there, I want to move on to some problems from the back of the end of the chapter, not the back of the chapter, the end of the chapter. And we're going to take a look at some nomenclature problems in a bit, but I want to just, keep on this train of thought of reactions. And I want to look at a question that involves a mechanism, which I think is a kind of a cool mechanism. And this is question 12.38. And I implore you to not look in the solutions manual, because this isn't a long mechanism, but it's an interesting one. And it also kind of is a good segue into the chemistry that you're going to see in the next chapter. So you're starting it with this bifunctional compound. You've got an alcohol and you've got an alkyl halide in the same molecule. And then it says, draw a mechanism for this reaction. You're going to treat it with sodium hydride, NaH, and you're going to end up making this cool molecule. Just a 6-membered ring with an oxygen in it. Well, how the heck is this going to happen? Could anybody give me an idea where you would start with a mechanism, or what you think might happen first without looking at the solutions? I'll let you think about it. This is a question I asked on a quiz a number of years ago, I remember. Thought it was such a great problem. What if we think about drawing our sodium hydride, converting our hydroxyl to water that attacks the. So we're not going to convert the hydroxyl to water because we're using sodium hydride. Right? If you were to take sodium hydride and put it in water, the hydride would just deprotonate the water to give you hydroxide. You'd end up with sodium hydroxide then. But what if we draw the Lewis structure of sodium hydride? Right, let's try that. So if we draw sodium plus and hydride minus, well, the hydride can act as a base, can't it? So if we have the hydroxyl, remember that we can deprotonate the hydroxyl with the hydride, right? We can take this and it's going to abstract this proton, put in my lone pairs here. There we go. And then it's going to break that bond, and then you're going to end up with this molecule. So you've got the bromine, you've got 1, 2, 3, 4, 5 carbons, and then you've got an alkoxide like this. You've also produced hydrogen gas, which is just going to go up into the atmosphere, and you have the sodium cation, which we normally leave out. So I'll erase that. So now look what you've got. You've got a nucleophile, okay? It's also a base, but it's a nucleophile. And then since you have a dipole here, right, this is an electrophilic carbon. This is your electrophile here. And they're in the same molecule. And so to draw the curved arrow, you draw the nucleophile attacking the electrophile. So you have the nucleophilic attack and loss of leaving group occurring simultaneously. And then look, you end up forming a 6-membered ring. Look, if we count up all the atoms that would be in the ring, and we would have a total of 1, 2, 3, 4, 5, 6. And that's why we end up with 1, 2, 3, 4, 5, 6. All right, and you end up making an ether. And again, if you look at the schedule, you see that in chapter 13, we spent a lot of, or we will spend, I should say, a lot of time talking about ethers. Let's try question 12.46, which also deals with mechanisms, and it deals with the mechanisms of Grignards. And the second one especially is important that you're able to draw. So let's start with 12.46a, which is the easier of the two, I would say. Of course, nothing's easy, but it's definitely the easier of the two. So we're starting it with a ketone. So this is called cyclohexanone, and we're treating this with methyl magnesium bromide. So one is methyl magnesium bromide. And then in the second step, we're going to treat that with water. And we're going to end up with this tertiary alcohol here. So a methyl group. There we go, like that. Well, let's draw out our mechanism. We can treat the methyl magnesium bromide as if we have a methyl carbanion like that, right? There we go. And of course, we also have the counter ion. I'm not going to worry about that because it's not participating in the mechanism. But we have our nucleophile. It's going to attack the electrophilic carbon, and we're going to end up making an alkoxide. So let's draw that alkoxide that's formed. There we go, our 6-membered ring. We have our methyl group, and then we have our oxygen that has our negative charge. And then in the next step, we're going to treat that with water. We'll draw the Lewis structure of water, like that. There we go. And then we're just going to do a proton transfer like that. So there you have it. That's the mechanism for this reaction, where we take this ketone and we convert it into this tertiary alcohol. Well, the next one is a little more involved. It's B, where we start with a cyclic ester. So I'm going to give myself plenty of room here. This is 12.46B. We start with this cyclic ester. Put my oxygen in the ring here. There we go. When you have a cyclic ester, it's got a special name. It's called a lactone. Lactone. Again, you don't need to know that for the next quiz. Man, I got to try to beautify this some. There we go. All right, there we go. We have our lactone. And then what we're going to do is we're going to treat this with excess methyl magnesium bromide. In the second step, we're going to treat it with water. And then we get a molecule that has no cyclic structure to it whatsoever. So we have 1, 2, 3, 4, 5 carbons, and then we have another hydroxyl. and then we have a geminal dimethyl like this. This is one of those kind of examples of a problem that might not look, you might look at it and say, how am I going to get from here to here, right? I don't know how to do that. Well, if you take it stepwise, you know, just think about it one step at a time, it will kind of unfold itself in front of you. So if we take our carbanion and we start with a nucleophilic attack like that, because we know that's going to be the first step. Let's draw what you're going to get from that. You're going to end up with an alkoxide. It looks like this. Put my oxygen over here. My oxygen that's in the ring. There's my oxygen with a negative charge, and there's my CH3 group. Well, remember that an alkoxide isn't a good leaving group, but remember this is the high energy intermediate that's formed when we do that first nucleophilic attack on an ester. So we can lose this oxygen as a leaving group. Let me fit in my lone pairs. And let's draw what you would get from this. Now, this is an example of where you have to count your carbons very carefully. Now, look, we're making a bond here between this oxygen and this carbon, and we're breaking this bond here. So we're going to have a methyl ketone right here. Then we're going to have 1, 2, 3, 4 carbons after the methyl ketone. Then we'll have our alkoxide. Let's try and draw it. So you're going to have a methyl ketone. So I'll draw it the way that it's done here. There you go. There's that pi bond that you end up forming. Now you've got 2 lone pairs. Then you have 1, 2, 3, 4. Let me make sure I get 1, 2, 3, 4. There you go. And then you have an oxygen with a negative charge like that. But remember, you're treating this with excess methyl magnesium bromide. So you have more than one equivalent. Now you've got another, or you've got an intermediate that's got a ketone in it. So what's going to happen there? I could end up doing another nucleophilic attack. Let's draw what that looks like. I'm going to have another molecule of my, let me draw it like this, I guess, of my Grignard reagent, which is going to do a nucleophilic attack like this. And now look what you've got. You've got the alkoxide that's going to end up being formed. You've got the first methyl group, and you've got a second methyl group. Then you have all those 1, 2, 3, 4, and you've got this here, like that. Now look at the final product, and look what we have drawn here. Okay, we have the correct number of carbons, right? This geminal, let me move this over here. This geminal methyl dimethyl is the same ones here. So all we have to do is take this in the last step, and we're just going to treat it with water, right? We're going to treat this with water, and there's going to be 2 proton transfers occurring simultaneously. We're going to end up taking a proton from here, and then we're going to have another molecule of water. And you could draw these out stepwise. I think in the book it probably draws them one at a time, but just in the interest of time and just to save us a little bit of space here, there you go. And that's going to give us our final product. So we'll say each one of these proton transfers, so we'll say proton transfers occur stepwise, not simultaneously. Anyhow, there you go. Give me a thumbs up if you follow me on that one. That one is challenging, you know, because you're starting with a cyclic ester, and when you go back into our textbook, we didn't look at cyclic esters necessarily. Is everybody with me on that one? Great, great. And that's an important question. Don't think like, oh, that's a question he would never ask. No, that's definitely an important question. In fact, I think I've asked a question very close to that on one of our previous exams. So what we're going to do now is we are going to